most important crucial rare earth element which is known as gadolinium. So how to recover gadolinium from a patient MRI urine? So that's like we are literally flushing the urine and we are capturing that gadolinium from the urine. So it seems to like flush to fortune. So welcome once again. So as you by this time most of the people must be aware of what are rare earth elements, what are the critical minerals, what are the critical minerals, how do you classify them, and how to what are the applications and everything. So in a brief, so lanthanum to lutetium plus scandium plus yttrium is classified as a rare earth elements, and in that lanthanum to samarium is known as light rare earth elements, and europium to lutetium is considered as a heavy rare earth element. But here in this presentation I am going to discuss specifically important one of the thing is gadolinium. So if you see the 17 rare earth elements, each element has its unique application or unique importance, whether it one of them used as a satellites, one of them used as a magnets. So what makes gadolinium one of its specialty? So where are they being applied? So how do we recover this gadolinium? So what are its sources? So what are the methods we used, and how much we able to capture from the urine? So these are the things I'm going to discuss in this slide. So gadolinium, so the atomic mass weight is 156.25. It sits exactly in the middle of the 17 rare earth elements from the lanthanum to lutetium, and it is classified as a heavy rare earth elements. So if you see properly the atomic configuration of gadolinium, which is xenon 4f7 5d1 6s2. So if you see carefully, there are 7 unpaired electrons in the orbital. So what does it mean? It means there are 7 unoccupied electrons, so it hasn't been paired. So what makes it special is it is the one of the most paramagnetic element in the atomic atomic table. So these 7 unpaired electrons will behave as a tiny magnets under the external magnetic field. So gadolinium is kind of a most paramagnetic element in the periodic table. And also, like if you see the atomic radius from the left to right in the increasing order, it sits exactly in the middle from 57 to 71. So it's neither classified as a too small or a too big element. So why it is important? Once again, the atomic radius. So it is important in one of the major context. So when the atomic radius is small, it is very difficult to attach with a bigger molecule or chelate with a different bigger molecule. When the atomic radius is too big, once again, and also it has a difficult to like attach with the bigger molecules. So gadolinium sits exactly in the middle of the 17 rare earth elements, and it is the most paramagnetic element being in the rare earth elements. So it is being used as a contrasting agent. So I will discuss in the next slide. So because of its unique properties, so it is been used to contrast some of the things in our human body. Again, going back to the basics, so we are seeing that figure as a simple MRI scan. So what exactly is happening in MRI? So why gadolinium is used in MRIs? So if you see that figure on the top right corner, so the left hand side is without using gadolinium or contrasting agent, and the right hand, as soon as you inject the gadolinium, you notice the tumor. So what does it mean? So this contrasting agent helps us to indicate or to differentiate the abnormalities in a tissues or abnormalities in a body. So without contrasting agents, all the tissues in our body remains same. It's very difficult to identify which tissue or which organ is being abnormal or normal. So those are known as contrasting agents. So anyone here like have ever been to the MRI before? Like have ever been done MRI before? Yeah. So whenever you are going to an MRI, so doctor first he examines you and he prescribe you like a contrasting agent. So he will inject a small injection, whether in terms of like a saline or some kind of injection. So these are known as contrasting agents. So these are made up of gadolinium complexes. So when you inject these into the body, it makes abnormalities things brighter, sharper. So why it is happening like this? If you see like a proper MRI designs or mechanisms, so MRI create a temporary magnetic field in the body. So whenever under the magnetic field, so these paramagnetic elements become very crucial. So our human body is made up of 70% of water and other tissues. If you see the water, there are more hydrogen ions. So more hydrogen ions, more protons, more paramagnetic. So in order to contrast between abnormalities and the normal tissues, we have to decrease an important factor known as relaxation time, at which the organs relax and produce the energy. So that's why you are pumping externally these gadolinium contrasting agents that extra pushes the more protons, more unpaired electrons, more paramagnetic in nature, more response to the MRI, and more contrast it will give to the abnormal tissues. That's how this has been used for MRI agents as a contrasting agents. That means it contrasts the abnormalities and the normal tissues. So if you see the overall world, there are only 8 approved FDA's contrasting agents. So each has its brand name and generic names. So wherever you go to the hospital, so these are the 8 injections. They choose one of the 8, depends upon the like the company availability and availability of the injection, and it depends upon the doctor prescription. You have been advised to take one of the injection before doing an MRI. So these are the 8, and mostly used two MRI contrasting agents are doTERM and Gadavist. You can see this structural. So I have a question like gadolinium is a metal. So if you import metal directly into the blood or body, like does it cause us toxicity? A general question for all the audience. So the answer is yes. So that's why what we do is we chelate, we complex with a bigger molecules are known as chelating agents. You see this, the gadolinium forms as a central atom, and it chelates with all those nitrogen and oxygen, and it forms a bigger molecule, and they have been patented for each and every molecule with a generic names. Same thing with, you see the gadavist, the gadolinium forms in the middle and it chelates with the larger complex molecules. So that's how it becomes stability. So when gadolinium becomes stable with other bigger molecules, it's very, very difficult to break the complex. So those are like a higher atomic molecules. For example, like in the molar masses of 700 or 800 and 900, it's very, very difficult to break this huge complex. So that's why it sits for in a body for some period of time without breaking, are more stable. So that's where the gadolinium is also very important factor known as ionic radius. That's why it's able to chelate with the bigger molecules and form a stable complexes, so that it will remain stable in a human body for certain period of time. So that's how the gadolinium is very crucial for some of the most important thing, MRI agents. So all here are 8 MRI agents are based upon only single molecule gadolinium. So no other gadolinium or no other element is used as a contrasting agent across the many countries. So the approved dosage is 0.1 millimolar of gadolinium per 1 kilogram of body weight. So if you take an average human body weights by the classifications, you see in the table, that is the milligram of dosage that the hospital or a doctor will inject into the human body. Say my body weight is a 600 or a 60 kilos or a 65. So whereas it's exactly around like for each human body, averagely they are injecting 1.1 grams of gadolinium, which sounds like a small number. But let me explain in a larger context. If you see like a overall mapping across the world, there are like most of them is untracked data. For example, in Indian or Asian countries like India and China, we don't have enough data of like how many MRI agents has been given and what is their fate and what are the transport of these MRI contrasting agents. Plus, there are some Western countries, for example, like European, Canada, and USA, they track each and every MRI contrasting agent. If you see like on an average human body takes 1.1 gadolinium grams of gadolinium per human scan. Think about like averagely there are 30 million MRIs are doing per year. So which is, if you calculate the number of kilos or tons, the gadolinium concentrations are like exact in European is around 20 tons in a 1 year, and US constitutes around 21 tons. And now I'm leaving you like what is the amount of MRIs or gadoliniums present in India and China. So it's beyond the number and it's like a huge quantity. So where exactly these are all going? So this is designed so that whenever it goes into the body, it stays into the body for some time, and during urination and fecus, it enters into the wastewater. That's how these are designed. So ultimately, all these tons and tons of gadolinium is reaching only to the wastewater or the sewers. So what is the fate of this gadolinium? So if you see, like, gadolinium is also one of the rare earth elements. Where do we get this? We mine. We mine it from the primary sources or secondary sources. So once it is mined, it is made it to the hospital in form of complex agents. So the doctor will give the patient the complexing agent. Patient happily goes for MRI. He takes MRI and he goes to the home and he started peeing or urination, and within first 24 to 48 hours he releases 98% of the gadolinium through urination and fecal material, and it enters into the sewage. But conventionally, all around the world, there have been reported only 10% of the gadolinium can be removed by conventional sewage treatment. So where all this 90% going? Ultimately, it is going to the waters or a groundwater, and fishes are eating it, and plants are uptaking it. Again, humans are consuming. It's part of a biocycle or a bioaccumulation. So it is all started accumulating in a human bodies by unknowingly. So this is known as gadolinium anomaly. So by unknowingly we are taking the gadolinium to the human body because none of the sewerage treatment plants has a capacity to remove the gadolinium. So 90% remains in the water or a plants or a fishes or any other things. For irrigation, again it comes to the human body. So this is the cycle of gadolinium, one of the rare earth elements which is used in MRIs as a contrasting agent. So what exactly we have been doing? So one of the hospitals, like where I'm working in US, has been reported excessive gadoliniums in the urine. So we have been taken this project as part of funding, and our main motive is, so once it imparts to the patient, and we have been given, like, our ultimate is to design the filters. So the patient will be giving a filters. So he pees directly into the filters. We separate that urination and we capture gadolinium by using the filters. Again, we recycle or resell gadolinium to the companies. So that is the overall ultimate aim. So by doing this, the urine is safe for discharge, and also we are getting more money by selling gadolinium back to the companies. So that is the overall motive. So our engineering application here is to design the filters or to design the packed columns for capturing selectively gadolinium from the urine. So urine is a very complex, again. It has a calcium, magnesium, aluminum, silic, and it has much more. It is very convoluted and complex, and gadolinium is only a one tiny part of the urine. Let's see, like, suppose if I'm going for a fishing, and in a sea you have a multiple and millions of fishes, and you want to capture exactly like a very similar or the like fish you want. So that's how it is difficulty. In a ocean of metals, you need to selectively capture one gadolinium from the urine. It makes the project and also like very tricky to develop like selective recovery of gadolinium from the urine. So that's how the project and the hypothesis of this small project has been made. So as part of the project, we choose one of the patient and we kept his all details confidentiality, and we have given some collecting tubes. So we selected, and he has been given MRI contrasting agents. We noted down how much we have been given by using the doctors, and we gave like 7 or 8 tubes. So the patient was given MRI around 10 a.m. and we started collecting the first urine at 11:58 a.m. So we collected all the urines where he is pissing for almost 24 hours, starting from 11:58 to 11:45 the next day. So we collected total 6 or 7 urine samples wherever, and we took so this is a biohazard sample. So we followed all the precautions, all the safety procedures, all the sampling, handling, and everything were done by according to the rules. Then we collected, and for simplicity we divided into number of tubes for ease of storage. We measured the pH, we observed the physical nature of the urine, and we stored the sample in a appropriate conditions. So why this is, again, I mean to say, going back to urine, why urine is so much complicated. So in order to prove or develop a proof of concept, we need to work even on synthetic urine and also the real urine. So real urine works. First, we cannot for a lab studies. First, we need to develop a media, and we need to what is simulate the real urine in the lab by using synthetic urine. Then, if it is success, then we'll use that media for the real urine. So the real urine sample are very precious for us. So we don't get another chance or another shot. So that's why in a lab we developed the synthetic urine, which exactly simulates the real urine in the field. You see, these are all the materials it goes to the synthetic urine. It contains huge amount of urea, potassium, sodium, citrate, creatinine, uric acid, urea, and magnesium chloride, oxalate. So it is according to the NIH norms. So these contain specific number of concentrations. So it took so many days to prepare a synthetic urine, and we made a synthetic urine in order to simulate the real urine in the field. And now we can imagine like how complex is the human body urine is, and how complex is to selectively take gadolinium from the urine, right? So now we have two urines, synthetic urine and one real urine samples. Now our design or our idea is to like how do we design a filter media or adsorbent media or a sorbent media for selectively capture of gadolinium. How do we choose? So before choosing, I need to know what is there in the urine first. What is the gadolinium concentration is there in the urine? What is the mass of gadolinium present in the urine? So before getting that, it's not appropriate to design any sorbent material. So I need to know what is there exactly in the urine so that I design my media or a filter media according to its capacity or selectivity. So as I mentioned before, we collected 6 urine samples and we did ICP-MS analysis for all the metals, including like 4850 analysis, and these are the gadolinium concentrations found in the urine samples. You can see like the left hand side indicates at 11:58 a.m. the first urination event has around 3200 ppm almost, which is like 3.2 grams of gadolinium per liter of urine. And as you see, like as the urination event passes, the capacity or the concentration decreases. Same thing, if we convert this concentration into how many milligrams of gadolinium releases, we can see almost in a first urination event, 750 milligrams of gadolinium is being released. If I want this concentration to be compared, for example, to the rare earth elements, all rare earth elements combined in fly ash, it's around only 200 ppm or 300 or 400 max. But in a single shot, we are getting gadolinium around 3500 or 3000 ppm. This is for a normal average human body. In some of the literature, they reported they have found around 20,000, 22,000, 25,000 ppm concentration of gadolinium in the urine. So what does it indicates? So as a designer or as a designer for a filter media, so what does indicates? If you see properly that the first urination event is itself 80% or 90% of the total concentration. So there is always a chance of source separation. So if individually take these things and separate only the first tube, we are eliminating risk of 80 to 90%. And remaining thing is all about 10 to 20%. So 80 to 90% of the money, 80 to 90% of the concentration and the work only goes for a single tube. And the single tube is the first urination, which is the primary and the most important thing in the collection and the processing. So once we got to know like how much of thing present in the urine, next we face so many complexes. As I mentioned, it's a very complex. Urine is a complex. It has many complex materials, and the first step is we need to break this complex because it's very difficult. It is a very higher atomic number. It is like a 700, 800 atomic mass number. It's not easy to absorb any of the existing materials. So the first difficulties we faced is how to break these complex molecules, how to absorb these molecules with some of the adsorbents. We tested 10s, 20s, 30s different types of media which are available, and every time we failed because none of them are able to break and absorb this huge complex material. So then what we did is we simply acidify the urine. So once we add acid or acidify the urine, it started to break this complex and release this free gadolinium in the urine. So once we release this free gadolinium in the urine, it's easy to develop a material and capture. Now the next question is, sir, it is acidified. It is very difficult to capture or develop a material in a huge acidic medium, because most of the adsorbents or most of the materials developed are works on only pH 1 to 5. Since we are acidifying, it went to the pH around less than 0 to the 4, 8, all the way to 4 molar or 4 molar sulfuric acid or a nitric acid. So it's very difficult for us to develop a material which works on this extreme acidic conditions. So again, we went back to the basics, literatures, screened many materials. Finally, we came up uh, one of the important ligand or one of the material known as TODGA. So this is one of the very important thing in the material. It is known as TODG. So it is known as NNN tetraoctyl diglycolamide. So it is belongs to one of the diglycolamides family, and this is conventionally used in many national laboratories for separating uraniums and separating nuclear waste from the things. So what speciality about this is it works in only extreme acidic nature. So it chelates very good in extremely acidic nature. That's why we choose that as a primary ligand or a primary adsorbent material to selectively remove the gadolinium from the urine. So once we got this chelating material, we coated in a solid support. So what are solid support means? Solid support are inorganic materials which are used as a base material in order to to attach the bigger molecules onto the smaller molecules or similar molecules. This has a very high surface area, around 600 meter square per gram. So what does it has is, or it has a hydrophobic surfaces, and this ligand we choose has a hydrophobic surface. It's like a head to head attachment. All the head chains, all the hydrophobic chains is attached to the hydrophobic chains to form a strong chelating complex adsorbing material which can absorb the gadolinium in the urine in a strong acidic nature. That's how we design this TODGA organosilicon media, which is known as TODGA media in a simpler terms. So that's how we made a filter media or a sorbent media or adsorbent media. So that's a TODGA organosilicon media. And this is a simpler procedure to coat. So first we take a ligand, we dissolve in any methanol or any acetone or anything. So after dissolving, we add a solid support. Once we add solid support, we mix it for thoroughly for overnight or some period of time. Then we evaporate the media, and finally we get the solid support or a solid supported ligand media. That's how we make a media in a very attach a media to the solid support. So once we attach to the solid support, we started doing absorption. Like we add some solid, we add urine to it, and we take a sample at regular intervals of time. We started with all the way from 30 minutes, 1 hour, 2 hours, 4 hours, 6 hours, 8 hours. We went all the way to like a 144 hours. So at each point of time, how much it is able to remove and what is its kinetics, how fast it is removing, how fast it is absorbing onto the media, and how it is modeling. So the left hand figure shows the this is for the normal urine, like a real urine, and the right hand shows for a synthetic urine. So we have simulated for the synthetic and real urine, and the good news is we exactly fitted a very similar kinetics and very similar absorbing nature, but for both real and synthetic urine. And it takes almost 24 to 48 hours to take complete gadolinium from the urine and to reach the saturation or equilibrium. From 24 to 48 hours onwards, it remains stable at a capacity of 10 or 11 milligrams per gram, which is exactly for the synthetic urine. That means our system is started working. It is able to remove all the gadolinium from the urine, and it simulates exactly, behaves good in both real and synthetic urine conditions. So once we get this, we want to have a proof of concept. Like this is an experiment. No one believes if I'm being captured the gadolinium or not. So how do you prove that? So we have like some analytical techniques. We prove that the system or developed media has attaching or absorbing the gadolinium from the urine. Say the top left hand is on a before adsorption. It's a simple XRF graph for finding what is the percentage of each oxides present in the urine. You can see the pink color, the gadolinium in the urine, like before adsorption, we didn't have anything. So after adsorption onto the media, we have recorded around 6.59% of gadolinium present onto the solid support or adsorbing material. So very similar results were found by using SCM and EDS, where you can see before adsorption, it was 0 or below detection limits, which is 0.57. But after adsorbing, it is found to be approximately around I think we don't have a data here. So we here 5.65% of weight percentage, and before adsorption we didn't detect any gadolinium. That means we have a proof of concept. Now it is definitely we are confirming that our developed media is absorbing the gadolinium from both urine and the synthetic urine. So that's how we determine, will give like a 100% surety of like what exactly happening. So these are the media developed particles. You see like how much the smaller the size is here is around 20 micrometers. So these are very smaller in size, having a good functional groups that chelates only to the gadolinium complexes in the urine. So that's how we get a confirmation saying that our media, our filter media or adsorbent media is developed is having like high selectivity towards only gadolinium in the urine. So once we develop that batch studies, and we have to simulate in a real columns. So columns simulates exactly like a filtering media. So the columns are like a long cylindrical columns. So where we inlet and exit outlet will be there. In the inlet, we pass the urine, and then the outlet we also collect the urine, and we do like what is present in the initial concentration and what is present in the outside like a effluent concentrations. So the x-axis denotes the cumulative pore volumes and y-axis denotes the C by C naught. So this is the classic breakthrough curves simulation for a dynamic conditions. So urine is inserted here. You see the blue color ones and the red color and the black color. So the black color is the first cycle and the red color is the second cycle. And the third cycle is we developed with the synthetic urine. So the first cycle, you see the black color. So it enters into the column and it adsorbs into the column. It will not release. After some point of time, the breakthrough occurs, and the breakthrough means it reaches the capacity, then it starts slowly releasing again urine into the effluent, and the concentration peaks and it reaches the concentration C by C naught equals to 1. So that's how a classic breakthrough column works. That means that we are seeing again gadolinium concentrations in the urine. So similarly, once it reached the peak, then we dispose or we release that attached gadolinium by using the water. We flush the water and we collect all the absorbed, all the captured urine into the water. So now we got a clear and only pure form of gadolinium into the water. Once we get into the water, it's very easy to make it into the purity. For purity, what we do, the next step is as I mentioned before, it has a huge amount of calcium. How do I know whether the calcium is also attaching into the filter media? So again, we run the columns. Next, we denoted like calcium and magnesium. What is the breakthrough comes? You can see that there is a sudden spike in the adsorption from 0 to 1. That means the column is not at all adsorbing. So the inlet and outlet concentration, it suddenly spikes. So that means that it is used as a one of the media is only selectively capturing gadolinium. It doesn't bother about anything. It doesn't bother about calcium. It doesn't bother about magnesium. So it enters to the column, it exits to the column. That's how you see the small or a sudden spike from 0 to C by C naught of 1. That is, these are the studies used as a tracer agents. So whenever you are getting in a doubts saying that whether our media is capturing or anything, we do this tracer studies, and magnesium and calcium is one of the tracer studies where we know like a quality studies where like is it selectively absorbing all these things or not. So we got confirmation the media is not at all bothering about all the competition. It is selectively taking gadolinium from the urine. So once we get all the pure urine in the water form, the next step is oxalate. So oxalate precipitations. So we have a gadolinium in the water. What do? We add oxalate and we raise the pH by using 5 using ammonium hydroxide. Then again we treat with 10% oxalic acid to make as a precipitate. Once we get the precipitate, we want to know what is there inside. You can see now the beautiful like gadolinium, oxygen and carbon. This is almost like a pure form of gadolinium precipitate. So in order to remove more precipitate and more simulations, we tested this with synthetic urine. So because synthetic urine, we can control the conditions, right? we can get in a huge quantities. So we spiked with gadolinium concentrations. We did similarly oxalate powders precipitation. We collected the precipitate and we did calcination. So once we get a precipitation, in order to get a pure form, we calcinate it. So once we got calcination, see the final product here. It has only gadolinium and oxygen, 86 and 12. That is the purest form of gadolinium. You will get like 99.2 or 99.3 percentage of gadolinium. So we got the pure gadolinium oxide powder, which can be sold or used for again contrasting agents. So this is the whole life cycle approach, or like a cycler approach of turning waste or a flush into the waste. Again we are using, and again we are like not contaminating the sewer systems or the waters. So this is the classic example of how do we take up a simple solution which is occurring in a field, how do you make a fortune out of that. So once we got a final product, now the next step is like we are also developing some of faster kinetics. So these adsorbent materials are slower, it takes 24 hours for absorption. So now we are developing a faster kinetics and faster filter medias and less acid usage. We are trying to recycle the acids. So this is still in the process of doing studies. So many people will ask, sir, I have an urine, so why don't I just do oxalate precipitation in the first step? Why not use only, like all these medias are developed, these are expensive, and these are like very, why do I need to run columns? Just I do directly oxalate precipitation and get the precipitate. Why can't I do? So the question is, we tried that also. We added directly the oxalate precipitation to directly to the urine and see what it has. It has sodium, aluminum, silica, calcium, magnesium. So it precipitated everything along with the gadolinium. Again, it forms complex, but the complex is not in a liquid now. It is in a solid form. Again, the similar story. So if we add directly oxalate precipitation to the urine, it forms a solid instead of liquid. So nothing will change. The story has to repeat again. It has to dissolve again into the acid, break the gadolinium complex, again do everything. So that's how our hypothesis worked, and that's how we developed the media for presenting the or absorbing the urine from the gadolinium and other sources. So if I see overall like a coordination chemistry or a complexing nature of a gadolinium, that's how it chelates. So it has a 3 Todga complexes, 1, 2, 3. And in a nitrate media, it captures only gadolinium by this specific oxygen-oxygen bond. So this fits exactly into the ionic radius of the gadolinium. That's why ionic radius again plays a crucial role in selectively capturing the gadolinium from the nitrate media in the urine solutions. So this is a simple case study of how we deal with the concentration. So our study is only 3000 ppm, but in reality, if you go and collect the urine from the MRA patients, you might get in 10,000s of ppm. That's a lot of money. So it's always so this has been published recently in the environmental chemistry letters. So if you are any interested, please refer to this journal. And thank you once again. I would like to acknowledge my old teammates and my funding agencies for providing this funding opportunity. And also I would like to thank Professor Narasimha and Professor Mohan and other colleagues for giving this opportunity for a short talk here. And I hope you like this small concept. Thank you very much. And yeah. So this media has been, so we used in a laboratory condition for three cycles. You see, the 3 cycles are giving a very similar efficiency, similar trends. So we are having a loss around less than 5 to 10% were reported in the capacities. So at least 3 cycles you have proved that it is reusable and recyclable. Yes, of course, we can regenerate, but regeneration has to be done. Still, you are working on that. So we tested till now is only 3 cycles because of our time considerations, and also, yeah. Any questions? Yes, adsorbent is a solid form. We pack that solid form in a media like a filter kind of thing in a columns. Then we pass the urine. Okay. Any questions? So the solid support will not triangle and no. Yes, solid support is basically inorganic material. So it doesn't have anything. So basically solid supports are designed to give as a base material for the ligand. So So we attach by hydrophobic, like a head attachments, so that it forms a strong chelating complex, and it is strong and stabilized in extreme acidic media also. So, and also Totga is a liquid. So in order to convert liquid to solid, we need a solid support. Yes. So this Totga is specifically designed for selectively capture of heavy rare earth elements. So since gadolinium is a part of heavy rare earth elements, it can easily absorb the heavy rare earth element. Yeah. So thank you everyone.
Thank you, sir. Such an interesting talk on gadolinium extraction.
Thank you so much.
So now let us take half an hour break and please go back for the